Hello, everyone. Welcome to this product launch webinar on the new multi-phase simulation capabilities in SimScale. I'm Kanchan Garg, your product manager at SimScale and one of your presenters for today. And joining me is my colleague, Jonas, who is an application engineer at SimScale. And we are both super excited to talk about SimScale's new multi-phase capabilities, which is something that we have worked for months to bring to Fusion. All right, so let's start with taking a quick look at the agenda for today's webinar. We'll start with going over the technology behind the cloud-native multi-phase capability, understanding how meshing, simulation, and post-processing happens. And this will be followed by a live platform demo by Jonas, where he'll use two industry cases to show you a step-by-step process of how you can set up and run multi-phase simulations in SimScale. But before we deep dive, a quick reminder to all of you that your mics are going to remain in mute throughout the webinar. If you have any questions, please do use the questions panel. At the end of the webinar, we will try to answer as many of them as time permits. And if you face any technical glitches, then also please use our chat option to get in touch with our webinar moderator. So for those of you who are new to SimScale, we are the world's first truly cloud-native simulation platform. Founded in 2012, SimScale now has over 400,000 users worldwide, and we are increasing this user base rapidly by staying true to our vision of empowering every engineer to innovate faster by making engineering simulation technically and economically accessible at any scale. Now, what that means is that with SimScale, there is absolutely zero hardware and software footprint. There is no complex licensing nuances, and it is possible to simulate a variety of physics all through your web browser within the hood of the same platform in a cost-effective manner, which means simulation can easily be scaled organizationally as well as computationally. And now in this webinar, what we're presenting is the combination of the power of SimScale's cloud-native environment with proprietary CFD technology, which we hope will unshackle the multi-phase industry and the multi-phase users from the constraints of HPC clusters, job schedulers, and most importantly, forever waiting for your simulation results to be ready. So let's see how that's possible. At the back end of the new multi-phase module is a proprietary volume of fluid algorithm that is developed by our partner Symerix Inc. It is pretty comprehensive in terms of the physics that it models, and the interface modeling itself is through a proprietary higher order reconstruction scheme that captures the interface really well, really sharply. And the methodology can handle all types of real fluid properties and give stable and fast convergence over a wide range of flow conditions and problem types. Now in CFD, there is usually a notion that there has to be a trade-off between speed and accuracy. Now, while we don't claim to be the know-all and end-all of CFD and to have everything good, but we do invest heavily in incorporating high-end methods and validating them for industry accuracy, be it for our customer cases or for standard benchmarks, while also leveraging our cloud platform, also leveraging high-end algorithms to speed up. So on your right here, you can see one such dam break analysis benchmark, where we compared the new multi-phase module in SimScale with PIV data for the experimental results, which was taken at many different points. And as you can see, the simulation results match very closely with experimental data, as well as the overall estimation of the flow patterns as compared with the actual flow. Experimental flow visualization is very good. And this is one of the problems that we have validated, which we're presenting for the brevity of time. Now, the new multi-phase module in SimScale is also very robust in handling intricate and complex geometries encountered in industrial applications. And why is that? Because at the back end, it uses a proprietary binary tree-based meshing technology that facilitates fast generation of Cartesian hex meshes which automatically adapts to the geometry surface and feature edges as it comes closer to the boundaries, and distributes the mesh cells in a very judicious manner without increasing the mesh size significantly. And additionally, users have controls like being able to add region refinement or switching to a more manual, more advanced mode should you need more granular control over the mesh. For example, on the radial gate problem that you see here, the entire mesh was generated using just one input, which is basically the setting the auto mesh level slider from the default value to 2. And on the top is what you see that you get with the automatic mesh settings. As you can see, all the features, all the thin channels or the thin edges of the sluice gates are well captured. Of course, for CFD accuracy, you would want to refine areas of interest more so that maybe if you want to look at the pressures and forces on the gates, and that is what you see at the bottom, which of course bumps up the mesh size. But overall, both of these meshes separately, if you look at them separately, both of these mesh generations could be done under 10 minutes. And another example I have here is for a heat exchanger, which has large tanks on both the sides with pretty thin channels, which are about a few centimeters apart. And just by changing the auto mesh level up to 5, we are able to capture all the features properly. And as you can see here on the right, and as a best practice, what we usually recommend is that when you have such thin gaps or thin channels, you should aim for at least 3 mesh cells across that width. And that is why we had to go up till the auto mesh level of 5. But the point to note here is that all of this is achieved just by changing one user input, and the mesh is generated within a few minutes. So there's a lot of time that is saved here. There is a lot of robustness that you can hope to achieve from the tool because there is minimal CAD cleanup. And all of this adds to a very fast simulation turnaround. So notably, the multiphase users one very big pain point that I have always heard is that simply the simulation turnaround time, the amount of time that users have to wait for the simulation to be over and for them to be able to analyze results and then move on to the next step of doing design iterations or uh, making further changes to their simulation. Now, as we saw earlier, with SimScale, you do not need HPCs, do not need job schedulers. And with this new multi-phase capability, you also do not need to wait days, let alone weeks, for obtaining your results. The CFD proprietary method that we talked about is inherently fast in terms of convergence. And when you combine it with the cloud architecture of SimScale, what it means is that you can obtain multi-phase simulations within few minutes, at max a few hours, depending on the problem and mesh size. And this is true also for design of experiments, not just single simulations, because being on the cloud, what that means is that the time it takes you for running one simulation, in the exact same time, you can run like multiple n number of simulations. And we do offer a lot of in-platform automation to launch DOIs and to do design studies, be it in terms of input parameterization, which you can do directly within the software, or API-based CAD parameterization, where you can connect your CAD tool with SimScale, or specific simulation templates for your specific problems, which allows you to make quick changes and launch multiple simulations simultaneously. So going back to my point about validating the new multiphase module for industry problems, you can see that here that we have done so for many different applications across industries. Point to note here is that because this is inherently a volume of fluid based approach, it does well in terms of accuracy and applicability for problems where the interface between the two phases is well defined. So, and those are the kind of problems that will be well managed across industries, across applications. And soon moving forward, we are also looking into integrating mixture multiphase models as well as particle modelings, where you can introduce solids within a fluid system. But let's not get ahead of ourselves. Let's focus now on this brand new capability. And with that, I will now hand over to Jonas, who's going to deep dive into the platform and show you everything that I talked about in a more hands-on fashion.
Thank you for this beautiful introduction on our new capabilities. So hello, everyone. I'm Ioannis. I'm an application engineer with SimScale, and I'm in the simulation industry for the past 6 years now. So what I prepare for today to show you, everyone, is we prepared a couple of use cases to exactly demonstrate our new multi-phase capabilities. So let's go ahead and see. So the first case we're going to be talking today is the optimization of a multi-intake tank filling process. So basically, what we have here is we have a feeding channel where it leads to the tank to be filled, right? And it's connected with it via these 7 nozzles. And then we have our main feeding nozzle here, where the liquid, or in this case, we just use water for demonstration, is fed into the channel and then led into the tank, right? The tank is open, so the feeding channel is open at the top to allow some communication with the open atmosphere. And typically, design goals for such cases is that the engineers would want to optimize the filling time, the filling process in general, and see how can they get the tank filled in the best optimum time, right? So we're gonna see how we can use SimScale to optimize this this procedure. So let me now exit my presentation and give you an idea about SimScale. So we are a fully web-based platform. All you have to do is go open a new tab and type simscale.com, and there you land at our main page. Then you just have to log in, as I did already, and go directly into your dashboard, right? So here I'm into my dashboard. I see all of my different projects. You see I have a couple of projects already here prepared. And this is fully web-based, fully cloud-based, meaning that there's no limit in the storage. Everything is stored in the web, in the cloud, right? So no one's gonna tell you, look, you have exceeded the amount of storage you can get. Please delete projects. No, that's not true. With SimScale, we offer unlimited storage to host all of your projects on the cloud. And the good thing is that these projects are accessible from anywhere in the world. You can, of course, work in teams, so you can create team spaces and share your projects with other colleagues, right? If you want someone else to have access and work on your projects, all those are collaboration capabilities enabled via SimScale and the power of the cloud. So for today, let's start with our first case, which is the filling a tank process that I have opened already here on my other screen. So let me bring it in. And what you now see, guys, is a peek from inside our SimScale project, and more specifically, we are already inside the post processor, right? So here I'm seeing the volume fraction of water, and we see that we're already into a couple of seconds inside the simulation. This is a total of 80 seconds simulated time, and we are currently viewing the results at the 63rd second, right? So we see we have the filling process, we have the water jet coming in. Probably some of it is also spilling out of the domain here. We can see some water spilling out. And then we can see how this is communicated to the main tank via these nozzles. What we can easily see in this image here is that we see some of our nozzles not working as expected. More specifically, nozzle 1 and 3 seem to have no water flow through them, and we have to know why. We have to inspect why this is happening. So for that, I can easily create a cut plane. I can hide the ISO volume now, and maybe to make it more easy to understand, I can clip the model with this cut plane, right? So now I'm plotting the velocity vectors as long as the velocity contours in this cut plane, and I can see that while 5 of my nozzles are working nicely, I see some velocities going through downwards, right? I can see the arrows. Then 2 of them are probably reversed, and I can confirm that by seeing the vector plots going upwards, right? So probably what's happening here, guys, is that I have some air trying to escape the tank and communicate to the atmosphere, right? So, all right, that already tells me my design is not good. I'm not getting advantage of the full nozzles. So maybe I have to do something. And if I want to be 100% sure about that, I can switch my results to the phase fraction, which now red means water, while blue means air. And if I zoom in here again, I see that those two channels, those two nozzles here are not working as expected. Let me go back to velocity really quick and show you what happens now if I create another cut plane. So I want to create a cut plane right at the center of the nozzles. And I can quickly explain what's happening here. And what's cool about SimScale is that I can use the statistics on this plane, and it will give me information about the actual flow rate, the actual mass flow rate going through its nozzle. So here I see negative flow rate, meaning that something is going probably upwards, while on this nozzle here, which is working nicely, I get 14 kilograms per second, which is good, right? It's partly water flowing downwards. I can download this data and do local post-processing if I like. That's good. And that can help me also identify that I don't have uniform flow between my nozzles, right? So now as an engineer, I want to do some corrective action here and say, okay, what can I improve to make this filling process more robust? Let's see how we can do it. But first, let's take a step back and see how we set up a simulation in the first place. So with SimScale, we start with a geometry, right? You can see here on the top left side. And all I have to do is go click plus button and I can upload my new geometry in the platform, right? We support all of the major formats, SolidWorks, Inventor, CATIA, but we also work with neutral formats like step file, ISS files, and Parasolid formats. So no matter what CAD you're using, you can easily work with SimScale. All you have to do is simply drag and drop your files. So as long as I'm happy with my geometry, I import it, I get it here in our platform. I can view inside, and I can then use our CAD mode to do some simple operations like moving faces, deleting objects, slicing parts, and extracting the fluid volume, which are really important steps for someone that works with the CFD simulation industry. Right? So we offer all of these smart tools that will help the engineers manipulate the geometry before it's ready for simulation. Now, say I'm happy with that one, let's go ahead and create a simulation. I hit the create button, and I get all of the different options. SimScale is a multi-physics platform. We do offer also structural analysis in the platform. But today, let's just focus on the multi-phase part. And for that one, in order to take advantage of the new multi-phase capabilities, you have to click on the subsonic option here, create a new simulation. This will give you a new branch in the simulation tree, all right? And then all you have to do, guys, is just start filling in the blanks and going from top to bottom and start checking what is missing. So let's first switch this to transient analysis, because multiphase is an inherently transient simulation type. And that will bring me the multiphase toggle, and I'll just set it to activate it. And now my next step would be to create the gravity. Gravity is really important for such cases where I have huge density differences between the two material. Let's just define the gravity towards the negative y-axis as it makes sense. And then there come the materials, right? So I click the plus button and get the material library. I can create my own custom materials if I like, but in this case, we just go with simple air. So I select air. We assign it to the fluid volume and say this is our zero phase, meaning our first phase, right? And then I'll also need water, which will serve as my second phase. I'll assign it to the fluid volume and assign it to the phase one. So now I've got my phases defined. And next step would be to create some initial conditions here. So probably this tank is already pre-filled with some liquid, right? It's not fully empty. So I want to set a certain fill level here, a fill height. So all I have to do is create an initialization of phase one. So I want to say water 100%, and I want to just put it at a certain height. So I can create a Cartesian box. I can use the smart selection tools here and put it inside the height, the domain and the height I want. So this is it. Ideally, I want this to extend slightly beyond the domain so that it covers all of it, but it's fine to go without right now. I'm happy with it. I click check, and now I have some water level already there, right? Already in the tank. Now, with respect to boundary conditions, it's very easy. Click the plus button. We need a velocity inlet where the flow enters. Here it is. And particularly in this case, we want to use the flow rate condition, and it's either mass flow or volumetric flow, depends on what data we have in our for our model, right? So in this case, I know the volumetric flow rate, and I can start with a single flow rate, let's say 0.1 cubic meters per second. Of course, I have to tell the solver this is water, so I send 100% water in this case, phase one. And now the next step is to say, all right, where the air exits. So I need to have an outlet as well to make it work, right? So in this case, I have an opening here in the top of the feeding channel. So it's sufficient if I just create a pressure outlet. Now in the simulation control, I have to tell the solver how much time I want to simulate and what the time step would be. In this case, I know roughly by experiments that this roughly takes, let's say 1 minute, maybe a bit more to be filled fully. So I'll say, okay, I want to simulate 80 seconds. And maybe I can go with a bit coarse time step, in this case, 0.1 seconds, since I don't really want to see the flow exactly how the flow goes inside the nozzle, but more or less I care about the greater picture of the full tank filling, right? So I'll say 0.1 seconds time step is fine. I can say I want to save my results every 20 seconds, let's say, and I'm good to start. As Kansan said in the first part of the simulation, we use an automatic measure, so we can easily play with the slider and adjust the fineness of the level of the simulation. And I'll just go with a medium fineness, in this case 3. But you can, of course, also add local refinements if you want to refine the regions around specific features. And that's basically it. I can go ahead and start. And I can start the analysis, right? So now I get a new run in the cloud. You can see it here running. I can shut down my machine and go do something else. So that's how I set up the first analysis, which, as it proved, it was a bit problematic. Now, what I want to do is, all right, take my template here, duplicate it. So this will create a copy of this template. I can name it new design. All the settings are preserved. And the smart thing is I can bring my new design variation, which is that one. It's basically the same model, but this time I included an opening here at the tank to allow some air to exit there instead of having to travel all the way up and exit from the top of the feeding channel. So I just hit check. The geometries are replaced. All of the settings remain there. We have smart cut associativity. All I have to do is just create a new pressure outlet and assign it to the new opening. And I'm good to start simulating without having to care about the other settings because everything is already assigned. So I click start and I get a new run with a new design. As a final step, I can also try another one. I can duplicate, I can bring in another variation, right? In this case, I've also included a deflector here, which will allow me to slightly increase the flow rate incoming inside the domain, because otherwise the jet would cause the water to flow outside the domain. That's something I don't want. So again, I just import the new design, click start simulation, and I get now 3 simulations running in parallel at the same time in the cloud. Now, if I go back and see some results, because I already solved these simulations for you guys, this is my new design variation. I go here in the results. I have already saved some animations. So we have the filling process here of the new design. This time you can see it's working better. All of my nozzles seems to be working, right? Probably, again, my first 3 nozzles over there are not performing so well. I see some disruption in the flow and some splashing, and maybe some air also tries to exit here, or maybe the water level is not sufficient to satisfy all of them. And then the next step I think, all right, is I have to increase the flow rate. I have to bring more water inside the feeding channel to let all the nozzles perform as expected, right? But then if I do it, I'll notice here that I get a lot of water spilled out of the domain, right? That's why I created the new design with a deflector. And this time, if I check the results, let's check the filling process. This time, the results are way better. You see the deflector allowed me to increase the flow rate. By the way, I used a like 80% greater flow rate this time. And I managed to have a certain level of liquid in the feeding channel, which allows me to have a uniform flow distribution among the 7 nozzles. So this helps me achieve proper filling within less than 80 seconds in this case. So that's all. For the first test case, we see how with multiple designs, we were able to study different configurations. What's the cool thing here is I can go back and say, all right, let me study other flow rates as well. I can create a parametric analysis. So instead of just studying one flow rate, I can say, look, I want to study a whole range of different flow rates. So I input a couple of them, I apply, and I create a new simulation. And this time, this will give me an experiment, meaning that instead of having one simulation running on the cloud like I did before, I now have 4 simulations running at the same time with a single click. So no matter if I have 1, 4, or 100, all of them will be run online in the cloud at the same time. So if one takes an hour, then all of them will roughly take the same amount of time. Now let's go back to the slides and summarize some of the results that we saw. All right, that's the first case. 2 of my nozzles not performing well. We see air flowing. Probably it's because this tank is fully watertight. This is not working. You see, I only achieve up to this point. Then with a new design, I'm adding an opening for the pressure to be relieved, and so air can exit. This time I managed to get a larger water volume inside the tank, but again, I have some issues with the uniformity of the flow through the nozzles. I don't get a uniform distribution of the flow. You see the first 3 nozzles underperform quite excessively while the rest are looking good. Still, it doesn't look good. Probably I have to increase the flow rate, but if I increase the flow rate, then I'll end up having all my water spilled out of the domain. So what I have to do is add a deflector and increase the flow rate by 80% and achieve a uniform filling process within less than 80 seconds. So really cool, right? So within few hours, I was able to optimize this design. Now let's go and look at a slightly more complicated case. Our second case is an industrial mixing tank case. And I say slightly more complicated because this time we also bring in rotating parts, moving equipment, right? And I just talk about the impellers, right? So we have our baseline design over here, guys, where we have 2 impellers and a simple tank. And then as an engineer, I want to study a new design variation where I want to bring in some baffles. I just want to test these rectangular baffles and slightly inclined position, but you can imagine the combinations are unlimited, right? I can test different tank shapes, like triangular tanks, rectangular tanks, doesn't matter. I can bring in different baffles, circular baffles, triangular baffles, change the angle of the baffles, the number of the baffles, the location of the impellers. I can study different RPM. So there are unlimited combinations of the amount of the geometric and flow combinations I can actually test in a design like that, right? My main goals would be to improve the mixing efficiency, study the power of the impellers that will tell me how much power I need to rotate these things and produce the required results, and identify any shortcomings in the mixing behavior, like if I have any recirculation zones, if I don't have proper mixing between the top and bottom part of the tank, which is really crucial for mixing applications and things like that. So as a designer, I want to study the behavior of my mixing and how efficient it is. So let's just go back to the platform again, go back to my dashboard. And here I have my other example, which is this one, the industrial tank mixing. And this time, let's just immediately start from the start. So let me grab the simple tank here I have imported. I create a simulation, subsonic. I'll be a bit quicker now with the steps because we already saw it once. Transient mode, have to switch on multiphase as we did before. And again, we have to bring in gravity, choose the materials. It's again air and water, or it might be another water-like material, like a slightly more viscous material, which is in this case. So again, go ahead, increase the density or the viscosity, but let's just leave it as that for now for simplicity. Then again, I have to patch the water volume at a certain level, which depicts the field height. In this case, I will use not a sphere, but I want to use a cylinder. I'll place the cylinder right on the center, switch the location, the orientation, and probably it needs to be a bit higher than the impeller, so I want to go up to 1.5 meters. Yeah, that looks better. I'm happy with my cylinder. I select it, and now I patch the water volume in this part. And then in terms of boundary conditions, I don't need anything, basically, because this is a fully closed tank, but I still need to assign the rotation to the rotating zone. So I select all of my rotating zones, like that. I should specify the correct rotation axis. In this case, is negative y-axis. And I just assign the rotation speed. If I have 200 RPM, then this is roughly 20 rads per second. Now, as a next step, I also care about the power needed for the impeller. So I want to create some result controls. And I select my first impeller, say impeller 1, align the center of rotation, and this will bring me the results of the force and moment plots while I'm running the simulation. I'll do the same for the second impeller. And I'm good to start. So again, let's use a medium S. And finally say, all right, I want to study 5 seconds would be fine. I can pick a flow rate. Let's just pick 5 milliseconds in this case. Normally in such cases where we have rotating equipment, we need to ensure that the time step won't be larger than a threshold where it ensures at most 3 degrees of rotation per time step. Let's see how that goes. So let me put this one and see if it works. I can go ahead and start a simulation. So let me see what I get here. SimScale gives me a warning. First warning I get is that my specified time step is that much. However, that's very large. You have to consider using a smaller time step, right? So that you ensure at most 3 degrees of rotation per time step. And then I also get an error which says, please ensure that every material corresponds to a unique phase. Probably I messed up something with the material assignment. I should go back and check. But the cool thing is that I can, SimScale will never let me run a simulation if something is wrong. It will always warn me. And if I have a question, I can use our built-in chat functionality and contact our technical support engineering team. And within literally a few minutes, I get an answer from our support experts. And all I have to do is check the button here so that they can have a look at my project. So no need to transfer any huge data, guys, through emails or through uploading services and everything. All of your data is there on the cloud, and we can immediately have access if you let us in, right? All your projects are private, but as long as you need support from us, guys, you can just check the box here, and we'll be able to have a look at the project. So let me see what I did here. Yes, this is it. I forgot to assign water to phase 1. And also I have to slightly reduce the time step so that it satisfies the best practice of 3 degrees per time step. So let's see. As this is it, I'm going to start. So I start a new simulation. And similar to what I did before, simply switch to a new geometry, bring the baffled design, and just run a new simulation, give it a name, say baffled design, and start. Simple as that. So let's check some results here. So in the first run, which is the plane design, I have created a couple of post-processing for you. All of this post-processing is stored here and can be accessed anywhere and anytime. So here is a free surface post-processing where we see this central vortex formed in this type of tank. Then I have a horizontal flow animation where we see that this type of analysis with just two impellers only creates a circular flow pattern, right? It doesn't let me actually mix the material from top to bottom, only gives me like a rotational mixing behavior, which might not be useful for my application. I can also do an ISO volume if I want to present some really nice animation and videos to my colleagues or to my customers. And then I can also visualize air and water. In this case, I just visualized air in red to highlight it. So this is the air on top. And I can see the central vortex that is actually sucking air inside the mixture, which might not be desired in some cases where I don't want air to entrain in my mixture and maybe harm the composition or affect the mixing performance. So probably this design won't be good for me if I just don't want air inside. So let's check the other one. So that one with the baffles. Let's take a look at the free surface. Now it's a bit different. I no longer get the vortex in the center because I have the baffle changing the flow behavior a bit. I get some entrainment here at the next to the baffles, but that's fine. It's not that big as it was before. In terms of the horizontal view flow, then you can see I no longer have a strong rotational flow, a strong swirling flow. Instead, I do get a more randomized flow, especially I can imagine here are the baffles, you can see them in background. At baffles level, I only get some random flow behavior, which is more precisely, it's definitely not rotational, but it's probably top to bottom down to the top behavior. So that's good. It promotes my mixing. Then the ISO volume also looks different. It's really good for using my reports. And again, finally, the water entrainment is no longer happening at the center, but instead it's happening now next to the baffles. But this is only for the first part of the simulation, then it will no longer happen. So that design is way better than the other in terms of air entrainment. Let's go back to the slides to summarize all of our results. So here, and of course, you'll get all this data, guys. You will provide you with the recording so you can take a look at the data on your own. We see all of the results summarized. So we see the free surface simulation for the two designs. We see the vector plots at the center plane, where we see this is a more uniform flow for the baseline design, while for the baffle design is more randomized, meaning that I most likely have better mixing behavior. And finally, I also see the air entrainment demonstrating here. What's really cool noting is that the when I don't use baffles, so in this case, I need less power to rotate my machinery here. So that might be something that someone needs to consider before going on and deciding which design they will go with. And again, to highlight here the complexity, this time it took us more time. While for the first example, it took us only 2 hours to simulate this filling channel. Here, we need a bit more time. It's 10 hours, mainly because we have this rotating motion, and we need to have a very fine mesh next to the blades so that we capture the behavior more precisely. So that one took more time, but that's not a problem. We can run 10, 20, 50 designs in parallel without issue, and all of them will complete in 10 hours approximately. Now, another view on the results. This is the baseline design with a swirling flow. We can see I mainly have a uniform behavior where I get downward motion at the center, and then next to the tank walls, I get upward motion. And that won't change no matter how I see the tank. Like wherever I put this cut plane, it will always give me the same results. While for the baffle design, I no longer get the swirling behavior here, the horizontal view, and still now I get some downward behavior, which is beneficial for my top to bottom mixing approach I want to follow. As a final step, and if you want to take it a step further, I added even more complexity to the model, and that took around 11 hours to run, roughly. So I added the sparger at the bottom. That's a device typically used in the mixing industry where they want to inject air inside the tank, and particularly when there is living organisms inside the liquid, like cells that need to be oxygenated. We need to ensure that there is proper aeration happening inside the fluid domain. And for that reason, we can use some spargers. Normally, we place them at the bottom of the tank, and we can also say to the software, okay, I want to inject some air. Just use an air boundary condition here, and see the bubbles forming. So that's how it would look like if we just put some air flowing through the sparge. So that concludes the live demonstration. I hope you enjoyed it, guys. Me and my colleague Hansen, we are open to any questions.
Yeah. Thank you, Jonas. I think that was really good and very smooth. And we do have a lot of questions coming up. Let me start by taking them one by one. Some of the questions we've already tried to answer in private chat, but I would still bring it up and discuss here so that everybody can benefit from the discussion. So the first question was about what do you mean by simulation at any scale in slide 2? Jonas, I'll take that question. So by scaling at what we mean is that because you're able to do high-end physics simulation from your web browser, you can actually, wherever you have an internet access with no latency issues, and you have access to a normal laptop and a web browser, you can carry out your simulations. So there is no constraint on your location or you having an access to any high performance machines. And because everything is on the cloud, your entire team, and in fact, across the teams, like between say design and engineering teams or other, even your customers can collaborate on your projects. So it is very easy to scale up the simulation work within your team, within your organization, and also computationally, because there is literally no limit on the storage that you can have on the cloud. Like you don't need to delete files or delete projects to make space. You also, there is a certain limit in terms of what your package is in terms of core hours, but that's also quite big, that allows you to do a very big or many number of simulations without always having to worry about resources. So that's what we mean by scaling simulation at any level. One question, probably Jonas, maybe if you can switch to the platform and show, it was about convergence. Like, how do we monitor convergence in the simulation? And if there is a way to actually specify.
All right, that's a nice question. Let me grab one of my solved cases here, and where I have a completed run. So here in the completed run, I have the converges plots. So we get the converges plots throughout the whole simulation time, right? And this is live during so as the simulation runs. Maybe I can also see it here. But as the simulation runs, you can see the convergence plots going along. And if you want to specify the convergence, you can do it already in the simulation control where you set the convergence criteria. So since it is a transient simulation, might be to go with 0.1 criteria. If you want to be a bit more strict on your convergence, you can go down to 0.01 or even finer. It's up to you to decide. In our best practice, we suggest typically what we see in the industry is 0.1 is sufficient for transient simulations, while for steady state, you have to go a bit more fine and go down to 0.001.
Okay. Yeah. Thank you, Jonas. And also one question about CAD was like, what are the different formats and different geometries that one could work with?
Okay, let me answer that right away. So as you see here, when I click the plus button next to the geometry, I get the import geometry dialog where it tells me what formats we support. So it's Parasolid, SolidWorks, Inventor, Rhino, CATIA, Creo, NX, Solid Edge, and Revit, but it's more. If you click this Learn More button, you'll be redirected to our documentation where you get more information about the actual CAD geometries we support and what is the actual import process.
Okay. What is the best way to evaluate multiple competing designs? Is there a way to see all simulations in one window?
All right. Also, nice question. Right now, we do support. Let me go here, for example, in this one, and grab one of my simulations, which is the tank filling we saw before. I'm reloading it. So we do have a comparison tool available inside the post processor, where you can use this tool to compare two designs, right? So you can see it here. You can let me bring some results. You can use the compare tool and compare this design to another design. Let's say that one. So this will give you a comparison on a side by side basis for two designs. If you have multiple ones, there is no direct way to do it. Maybe you can open many tabs and bring all the designs side by side. But right now, the direct comparison in the post processor, it's possible for two designs at a time. So it's loading a while. Hope that answers the question.
Yeah, definitely. Definitely.
There you go. So you can create a CAD plane and do all the comparison here, side by side.
Okay. And wonderful.
Thanks.
All right. So there was a question about talking about how the meshing technology for this new multiphase differs from Snappy Hex or for that of the other commercial software, and I'll take that, Jonas. So as I mentioned in my presentation, at the back end, this is a binary tree based mesher. So what it basically does is that it keeps on dividing the mesh cells in order to conform it to the surface, right? And the adjustment happens automatically rather than the user needing to go in and put patches or really handle sharp edges or some really small features. So this methodology is very good at modeling or capturing small gaps and small thin clearances, especially for example, the kind that you see in microfluidics or the kind that you see between the impeller and the casing. And so those are the sort of areas where Snappy Hex sometimes has problems. And especially when you go to transient simulations, the interpolation between the rotating and the stationary part is very smooth. And it has what is known as mismatch grid interfaces at the background, which automatically takes care of patching these different, stitching together these different patches in a very robust fashion. And because it's a binary tree methodology, what it also means is that from one mesh cell to the next, the aspect ratio is very good. It is 1:2, as against any other most other hex meshes where you may even have an aspect ratio of like 1:8. I hope that answers. And there is one question about, can we model three phases together like air, water, and oil? Not yet. You might have missed that in the slides that I showed. At the moment for this first release, we have enabled two-phase simulations, but it is completely possible in terms of the CFD solver. It is a generalized N-phase solver, and we have on the development side, we have tested it for more than two phases. In the coming months, very soon, you will hear an announcement of extending it truly for like more than two phases. And one question for you, perhaps, Yanis, is if we share a simulation project with the team, do the team members need a license too?
So let me go back to project, maybe that one. So you can share a project with your team members, right? You can type their emails or usernames here, and you can choose to give them view, copy, or edit access. If you want to give them edit access, then this implies that you need to have a license for the other team member as well. We didn't touch a bit on the licensing. Maybe that can be a different topic. We can give you more information about how licensing works. But if someone needs to edit the project, then he needs to have a license. What you can do, you can give only view access, and that could also work to someone with the community account. But then they can only view, right? Cannot do any copy or editing, and that's all.
Okay, thanks.
Mm-hmm.
We do have a follow-up question on the meshing. How controllable is the meshing?
All right.
Do you want to show that, like the two different modes that you can do?
Yeah, let me exit this view and show you an example of what I did here. So here we have the tank filling, right? And in this case, I went with the, you can either go with the automatic measure and just choose a fineness level, and then also add some region refinement. For example, in this case, I added some region refinement near my nozzles. So I want to refine the mesh next to them so that I get a proper capturing of the interface between the two faces, right? So I can create a limited number of refinement zones with a target mesh size, or else if I want to go a bit more advanced, I can switch to manual mode, and then I get more control. Like I get the minimum, maximum cell size, I get the sizing of the surfaces, and I can choose either to be relative or absolute to the CAD, and will of course bring in some changes on how the measure will work. But yeah, generally that's how it works. I would say 90% of our customers are happy with the automatic measure, and probably adding a couple, one or two refinement zones around the regions they want to get more detail. And then if you are more on the expert side and you want to go a bit deeper on the meshing, you are invited to use the manual measure, and so that you have more control.
Okay, great.
Hope this answers the question.
And, yeah, I think it does. And there's also a question about how is the integration, like can one export CAD and meshing to use in other simulation tools? Because often users or engineers have multiple tools, and perhaps I can answer that. It is totally possible. We have an open API uh, which allows us to integrate SimScale with any third-party tool. And in fact, we have in the past demonstrated such a use case with many different CAD tools as well as optimization tools, where you can also automate this process. So for example, if you have n different CAD geometries in your native CAD, you can, as long as the other tool also has an open API that can be linked against our API, it is possible to develop a small script, and our team usually helps our customers do this. We have a lot of customers who explore this, who leverage this workflow. And so there is a programmatic interface available for the API, and through that you can bring in CAD, run your simulations either in batch mode or within the platform, and also again export results or performance data, usually to 2D data, again to another tool or the same tool for further processing. Can you simply download the mesh generated by SimScale? No, you cannot. And then use in another CAE package. For our open form based solvers, we do give the option of downloading the results and mesh, which can then be usually analyzed in ParaView. For this proprietary solver, we don't yet have the option, but we are working on it, because a lot of times users want to download results, want to download mesh for, as you mentioned, for to be used with other tools, and sometimes simply for archiving purposes. So that's a feature that is often requested, and in future we will try to integrate that as well. But I doubt, because this is a very proprietary mesh data structure, it will not work with other CAE packages. But yes, you will be able to visualize the results in generic post processing tools. I think we have time for one final question, and that would be about the warning that everybody saw, Jonas, when you were setting up the time step for the rotating zone.
Hmm.
And maybe you don't necessarily need to go back to the demo, but maybe it would be worth clarifying here the difference between a warning and an error, and also
Yes.
the fact that the time step warning itself is only a best practice for rotating zones.
Yes. Yes, of course, Kansan. Yes. So, in SimScale, we built a smart way of doing simulation. And what you might have noticed when using other tools is you most of the times find yourself starting a simulation, then go to something else and come back after a few minutes and the simulation is crashed, right? And I'm not sure everyone has experienced that in the past, me, myself as well. With SimScale, we try to prevent this. So we try not to let you run a simulation if we think something is wrong. So if something is totally wrong and the simulation cannot start because it's going to crash right at the first time step, then we give you an error message, so meaning that something crucial is missing that might cause your simulation to diverge or not work at all, right? Or, for example, you missed, I don't know, some material property, or you have empty boundary conditions, or like you didn't create a mesh or something, right? So we will never let you run a simulation with an error. Then we have a lighter version of this system, or we call it a warning, of course, which is a light yellow coloring. And that's just the best practice advice we suggest you, so that we try to help you get the best results out of the simulation. For example, as we show in the warning message with the time step, we know from experience that when we're starting rotating machinery, like impellers, fans, pumps, etc., we need to have sufficient resolution, not only in the space but also in time, right? So typically, a best practice for that would be we need to at least have 3 degrees per time, right? We shouldn't let our machinery rotate by more than 3 degrees within a single time step, right? And we just put this information inside so that if you try to put a larger time step, we do some calculation in the background, calculate the rotation speed, the degrees and everything, and we give you a warning, okay, look, this time step is too big. Maybe you should consider lowering it a bit if you want to get best result. But this is just a warning. Of course, if you know what you're doing, you can skip this warning and just run the simulation.
Thanks, Jonas. And I think we just have time for one final question. Were there any suggestions about particles and powder mixing or plume geometry, for example? Yes, I did mention during my presentation that that's something that we are looking into, and in fact, it is on our short-term roadmap to integrate particulate matter, basically a discrete phase model, which would be able to handle low concentration solid particles within a fluid system. So stay tuned, I guess, for further updates. And unfortunately, we are almost out of time. Thank you all for joining us. It was a pleasure taking all these questions. And there is, of course, information on how you can sign up for SimScale if you want to try, or you can get in touch for a one-on-one demo. Thank you once again for joining us.
Thank you, everyone. Bye.